Hello, welcome to this session on water distribution system mathematics. I hope that this will be helpful for you to solve mathematics used in the industry out in the water treatment field and water distribution systems. Also help you study for your exams and maybe get ready for those word problems that are on the tests that some of us struggle with, and I know I have too. So my name is Ron Trigar. I'll be your host and facilitator today, and I hope that I can help you guys out with building up some of the confidence that you might need for solving some of these word problems. And we're going to be going quite in depth on some of these, and I hope that I can explain it enough for you all that you can relate to that, and we use real world examples that are relatable, and that you can see that the math is helpful and useful. Anyway, let's get started. I'm going to go ahead and share my screen, and we will get into the sessions. So, all right. So water distribution system mathematics covers a lot of material. Like you see in this picture, we have an operator flushing a hydrant, and there's math that goes into that, like how long would he flush a hydrant, or what velocity is moving through the pipe when we're flushing hydrants, or how long would it take to move a certain number of gallons of water through if we're trying to flush a nominal amount of water. So we're going to be kind of going into all of that today. So hopefully this will help you out. So we have a copyright statement for these sessions. University of Florida TRIO Center is a center for training, research, and education for environmental occupations. So just want to mention to you that these are reserved, all rights are reserved. No parts of the publication can be reproduced or copied or stored or transmitted without the official written permission of the University of Florida TRIO Center. My name is Ron Trigar. I'm a certified environmental trainer, and I work here at the University of Florida TRIO Center. I'm the senior training specialist for the water and wastewater treatment programs. I do a lot of the training for the operators to get ready for water and wastewater treatment exams and water distribution system exams. And we do a lot of training here for continuing education units towards those licenses. Do a lot of training to help people get ready for tests and all that, and just to know how to run their facilities. So this has been kind of an interesting year for us, coming out of the COVID pandemic and making a lot of recordings. So this is just one of a lot of recordings that we made for water treatment and wastewater treatment, mathematics, the supervision, and all that. You can check us out on the website, and I'll show you in just a minute where those other videos are. The University of Florida TRIO Center, my number is 352-294-3881, and my email address is rtrygar@trio.ufl.edu. And check our website out at www.uftrio.org. All right, so the video series that we're about to embark on is quite lengthy. There's a lot of math to cover, and we're going to go through the formula sheets and all that. And even in the very introduction, we're going to talk about problem solving with the functions of mathematics, multiplication, division, subtraction, all that kind of stuff, and what the order of operations are. We've broken this segment into categories. So in the at the beginning of each category, I'll take a little break for myself, and I suggest that you do too. After we get through some of these that are a little bit longer than others, you might need to get another cup of coffee or some 5-hour energy or something to keep yourself awake. We have about 7 topics total that'll be covered here, including, or on top of that, this brief introduction. So we have a lot to do. So the contents look like this. We have the section number 1 is area, circumference, volume, and gallons, and then even converting that into million gallons. We're going to talk about cubic yards, gallons of paint, tons of asphalt in the second section. Disinfection will be the third category. We're going to talk about how much chemical to use for disinfecting water mains and storage tanks, and chlorine residual and dosage and all that fun stuff. We will be getting on section 4 into pressure, velocity, flushing, and flow rates. That's a lot of pipe dimensions and cubic feet within a pipe, and calculating into gallons, and then figuring out how much water is moving through the pipes. So there's a lot to do there. And we're going to get into pumps and pumping. This will be more about the total dynamic head, or the water pressure that water's pumping against, so to speak. And we will talk about a question, or category number 6 will be accounting and administrative math. This will be kind of like some percentages, water loss, things like that. And then lastly, we have temperature conversions and any miscellaneous math that we have to add in here or there. So temperature conversions are sometimes seen on exams. So we'll go into those different ways to do Fahrenheit to centigrade or centigrade to Fahrenheit. All right, so supplies you're going to need for this, I would say pencils and erasers, maybe more erasers than pencils. I don't know. Paper, scratch paper, notebook paper, something that you can write on. You're going to need a calculator for sure. I suggest using a calculator that is something like what I'm going to pull out of my drawer here, because I forgot my calculator. So I would suggest using a calculator that's just a basic calculator. So I'm using one that's a little bit larger display. The buttons are a little bit larger here. I find that as I get older, my eyesight is certainly not as good as it used to be. So I need the bigger display. And I also need bigger buttons so that I don't kind of hit 2 or 3 buttons at the same time when I'm working some of this math, because you could easily hit 2 buttons at once on some of these small calculators. So just want to kind of show you that it should not be a scientific calculator for doing the math, especially for taking an exam. You might be questioned on having any kind of programmable calculators, and you certainly on exams can't use a cellular phone, the calculator built into your cellular phone, because these have cameras and all that. So exams are much more secure these days. So you can't bring in a cell phone. And if you're used to using your calculator on the cell phone, then I would say get yourself a calculator like this and just practice with it, because you're going to need that. Think about this as a tool that you're going to use to take an exam or work in the field. Think of this as a tool, just like any other tool that you would buy that you want to be comfortable with, and you want a tool that's going to be familiar to you and helpful. So I've kind of graduated, so to speak, to the old guy calculator that has a little bit larger buttons, and I just like it a little bit better. So anyway, you're going to need a calculator. Obviously, we're going to need some formula sheets, and I'll show you where you get those on our website or at the state DEP. You can get them in your state or in the state of Florida at our DEP office website. You're going to need some patience. Have some patience with me. We are going to start from the simple and work all our way to complex. So it means I'm going to start with just some basic figuring of area and shapes and, circular shapes, squares, cubes, rectangles, all that fun stuff. We're going to go from simple and work our way up to the more complex, but we can't do the complex until we get the simple foundation set first. So I want to make sure that we're all clear and everybody's on the same page before we go too far into some of this stuff. So have some patience with yourself and with me. And hopefully you have a desire to learn. If you're watching this video and you're saying, man, I want to practice this math and I want to get this stuff right, I want to make sure I can do this work in the field and be able to be a good water distribution system operator and be the best that you can be, and get those higher licenses and all that knocked out, a desire to learn is really important. So hopefully that's the motivation that you have, is to try to excel at what you're doing, and I want to help you with that. So our calculations or calculators are shown here. Dual power source, easy to read display. I like the larger buttons. They need to be non-programmable, especially for state exam or any kind of proctored exam situation. And be sure to practice with it before you take a test. There's nothing like buying a calculator on your way to sit for an exam, and then you take it out of the container that you got it in, the packaging, and it doesn't work, or you're not familiar with it. The buttons are in weird places, and they're just something that isn't comfortable for you. So practice with your calculator before you take any exam, or even just using it in the field. Get used to it, get comfortable with it. Like I said, think about it like a tool. If you have certain wrenches that you like, or certain pliers, or certain valve wrenches, or something that you're comfortable with, think about your calculator the same way. That's your tool that you're going to use. We have to follow what's known as the order of operations. And I want to kind of point this out to you guys before we get into these formula sheets. The more common thing, or the most common thing for us to do when working math, is to go from the left and work towards the right as we look at these equations or calculations we're going to do. And that's fine for most general purposes. But when we're working with these formulas that you're going to see on formula sheets, there's a definite pathway that needs to be followed to accurately calculate what we're going to be doing. And remember that an accurate calculation can mean the difference between underdosing chemicals or overdosing chemicals, or just not being able to get a question right out of a multiple choice, 4 multiple choice answers on an exam. So, you want to try to follow the functions of math, or the order of operations. So there's an acronym that we use called PEMDAS, or PEM, kind of underline it here, PEMDAS, and that stands for PEMDAS as an acronym. So where the letters are, P stands for parentheses. Anything in parentheses, we're going to work first. We're going to come down the list, and anything that's in an exponential form, we're going to work that next. We're going to do any multiplication, then division after that, addition, and then subtraction. So anything in parentheses should be calculated first, and then we do other orders of math or other functions of math afterwards. So if there's multiplication to be done, or division or subtraction, you will do anything in parentheses first and then those later. But if you have something that is subtraction inside of a parentheses, then we're going to do the subtraction in the parentheses first. So let me kind of show you what I mean by that. We have a couple examples here. By the way, some people remember this acronym PEMDAS as "Please excuse my dear Aunt Sally," which here we have somebody's dear Aunt Sally showing on there. So "Please excuse my dear Aunt Sally" is a way to remember parentheses, exponents, multiplication, division, addition, and then subtraction. All right, so here's an example. So which is correct? Is it 7 plus 8 times 3 equals 45, or is it 7 plus 8 times 3 equals 31? We see 2 different results here. So working from, like, say, left to right, in this direction, we would see 7 plus 8 is, we're going to make sure we're all on the same page. So 7 plus 8, 15, right? 15 times 3 is 45. So we're working from left to right, but we're doing the addition before the multiplication. Now, remember what PEMDAS says. PEMDAS says that we should do multiplication and then addition, right? So what we're going to do here is the multiplication first, and then add is the second method. Let's see what we get there. So 8 times 3 is 24. 24 plus 7, I get 31. So which one of these is correct? Well, following PEMDAS, we would see that the 31 value would be correct, because we're going to do the multiplication before the addition. So that's how we work that. So again, remember, follow the order of operations. We got another example here. Let's take a look at this next one. And this one is similar numbers. We have working from left to right, we have 7 plus 8 times 3 is 31, like we talked about just a minute ago. Or we have something in parentheses. We have a line of equation showing 7 plus 8 in parentheses times 3 equals 45. So which one is correct here? So if you're looking at those parentheses saying, well, anything in parentheses is done first. So remember, 7 plus 8 is 15. So we're going to do the 7 plus 8 first, and that's 15. And then after that, we do the 15 times 3, which then gives us the 45. So 15 times 3 is 45. So the second one, because of the parentheses, leads that line to be correct. So practice that. Watch out for those things. You're going to see that through our discussions today, and we'll be trying to show that as we go through. I'll kind of point those things out. The formula sheets we're using, because I'm working with the state of Florida type of exams here at the University of Florida Trio Center, we are using the state of Florida's DEP Operator Certification Program formula sheets that are approved for both the distribution system operators and the water treatment plant operators. So it's the same formula sheets that are given on our exams here in the state of Florida that are computer-based tests, or their paper formula sheets given at the exam site. So this depends on what exam site and what they're doing and what the proctors have available. So where do you get your copy at? Well, you can go to the Trio Center website at the link shown here, or it's just kind of written out for you in below where it says it's https /trio.ufl.edu/water wastewater /student resources. So if you go to the student resources page on the University of Florida Trio Center under the water and wastewater programs, you should see student resources link. And when you click on the link for student resources, you'll see this. So the drinking water resources are shown first. And if you scroll down, you're going to see these formula sheets, which are basically right here. Formula sheets are shown here, and you just click on those and it will give you the formula sheets. So here's a page of what one page of the formula sheets look like. This is page 1. There's actually 8 total pages, so there's a lot of formulas here. And what a lot of operators tell me, what a lot of water distribution operators and water treatment operators say is that, there's just so many formulas here. Do I have to know all these formulas? Or it looks intimidating when you see all these formulas because, it's got stuff like, all this alkalinity relationships and all. Do you need to know that as a water distribution operator? People tend to get a little panicked over, what is necessary for the exam and what's not necessary. So that's what I want to kind of alleviate some of that fear here today and point out some of the formulas that are most necessary for the water distribution exam. So let's kind of take a look at that. So on page 1 of the formula sheets, we have a conversion table, and I'm going to talk about that just a little bit here. So we do have some conversions that we have to know for water distribution exams. We also need to know area, circumference, and volume. And we mentioned that was going to be our first section, the first category. So we're going to talk about area, volume, cubic feet, and circumference, the distance around a shape. And on page 2 of the formula sheets, we see that we're going to need to know something about averaging, or the arithmetic mean, which is an average. We're going to not really need anything else off of page 2, I think, for your water distribution exam. I say most all of this is water treatment mathematics, and different levels of water treatment operators use different sets of formulas depending on the level of the exam you're taking. So water distribution folks, you can kind of say, well, on page 2, I only need the averaging. And on page 3, what do we need here? Well, on page 3, we're probably going to need to know something about the disinfection components. Like if we have a certain dosage and we have a residual, how much demand of chlorine was in the water. We're going to need to know something known as feed rate, pounds per day of chemicals. We're going to do that today. We're also going to go on to page 4. We're going to talk a little bit about using alternative chemicals for disinfection. Alternative chemicals would be something like calcium hypochlorite, which is commonly known as HTH, and sodium hypochlorite is commonly known as bleach. So we're going to talk about those today. And we're going to get into flow rates and velocity, either through pipelines or channels. And we're going to talk about flow rates. We're going to talk about flow rates as cubic feet per second, gallons per minute, and even velocity. And then on page 5, we're going to talk about the time for flushing a water main. We're going to get a little bit into parts per million and what dosage actually is. We're going to talk a little bit about pressure and head, which is the pressure of water in, say, an elevated storage tank or some kind of water column. And we're going to talk about the head and feet and convert that into feet or pressure, depending on which way we're trying to go. And we're going to be talking about pumps, which is going to be horsepower. We'll talk a little bit about that. And then page 6, what is on page 6? Well, right there at the top is total dynamic head. We use that a lot with pumping systems. So we're going to be discussing that. We might even get into the efficiency of the pump system. We call that wire to water. That is how efficient the actual voltage or the incoming current into a motor is being transformed into actual movable energy to make water flow through a pipe. So how efficient is that? And then we're going to talk about that today. And on the last page, we're going to talk about temperature conversions and a little bit about water loss. And let's see, I don't know if there's anything else on that one. I don't believe other than water production, we'll talk about volume of water produced a day. So we got a couple things here to talk about on that last page. And the very last page rather is page 8, which is just the abbreviation. So page 8 of 8 is some abbreviations. If you forget things like what HP stands for or GPM stands for, it has the actual abbreviations listed there. All right, so go back to our discussion on these conversion tables. So there's going to be some things you're going to have to remember for solving some of these equations, that some of these conversions have to be done first before you can launch into using some of the formulas on the other formula pages. So we're going to need to cover something known as how many inches are in a foot, or 1 foot is equal to how many inches, because pipes come in different inside diameters. We have water mains that are 8-inch water mains, 6-inch water mains, 2-inch water mains, 18-inch mains, 36-inch mains. A lot of the discussion about water mains and pipe sizes is usually in inches, and that's inches in inside diameter. So we're going to have to talk about converting things from inches into feet. We will definitely be talking about how many feet are in a mile, and we'll be dividing this into half-mile segments or quarter-mile segments if that's what our word problem tells us. We will be covering a cubic yard, what is actually a cubic yard, and how many cubic feet are inside of a cubic yard. We will be talking a lot about pounds of water in a cubic, or how many gallons are in a cubic foot, and then how many pounds are in 1 gallon of water. So we're going to talk a lot about those two conversions. And moving over to the other column, the third column over is PSI. I'm going to be covering how much 1 PSI is equal to 2.31 feet of water column over the pressure gauge. And then we'll also incorporate into that what 1 foot of water head and how many PSI that would be, as shown here. So we'll use those today. And over on the last column to my right, we're going to talk about 1 minute is 60 seconds. We're going to talk about 1 day is 1,440 minutes in a day. And let's see, a milligram per liter is equivalent to 1 part per million, because that is kind of where some people get a little confused when we're doing these calculations, because you'll see somewhere along the lines metric units will get converted somehow back into pounds, which are imperial units and the units that we use here in the US. So how does it go back and forth? Well, I'll describe that a little bit later, but essentially a milligram of something in a liter of water is the weight equivalent of a part of something in a million parts of water. So we'll discuss that a little bit later, but just want you to know that they equal each other. So if somebody says a ppm and you say, well, what is that in milligrams per liter? You say it's the same thing. All right, and 1 horsepower, we'll discuss this a little bit later. We're going to have a discussion about how many foot-pounds a minute are in 1 horsepower. That's 33,000, but that's incorporated into another calculation later on. So, all right, so let's take a look at how the conversions are used. I want to kind of describe to you that first off, there's more than one way to do some of these calculations that I'm going to show you. And because we have a limited amount of time and I don't want to guide you in too many different directions, I'm going to show you how I work the math on a lot of these formulas. You are certainly welcome to use other methods or take other routes to get to the same answer, as long as we're getting the same answer, as long as we're coming up with equal numbers or very close to each other. Maybe we're off by a little teeny bit because we rounded a little bit differently. Maybe you might round off a little differently than I do, but we basically should come up with the same answer no matter what procedure we take. So we're going to be using conversions to do some of this work. And this is just a visual image to describe to you what happens to a number or a value when we start multiplying by these different conversion numbers. numbers like 60 seconds in a minute or 60 minutes in an hour or 1,440 minutes in a day. It just kind of shows you from this little graph here, what happens to the number values. So if I start up at the top corner here and kind of point to this acronym or abbreviation, it says CFS. That's cubic feet per second. Notice that the box is essentially this size and this shape. So if we start multiplying into the cubic feet per second, if we start using multiplication factors, conversion factors, we're going to start getting larger and larger values. The actual numbers will get bigger. The values will get larger. So, for instance, if we have 1 cubic foot per second and we want that to be in cubic feet per minute, and we want to go this way into cubic feet per minute, we just multiply that number 1 by 60 seconds in a minute, and we'd end up with a larger value. So instead of just having 1 over here, now we have 60. So what happens if we say, well, I don't want just cubic feet per minute, I want cubic feet per day? So we multiply the 60 cubic feet per minute times 1440. And on your calculator, 60 times 1440, and I came up with 86,400. So over here now, all of a sudden, we're up to 86,400 way over here. And that number got much bigger, didn't it? So the actual little box right here, the actual box itself, the size got larger. So that's kind of how these work. And you can kind of see that there's multiple paths to get to the same answers. Like, to solve something like gallons per day or pounds per day, you can take all these different paths to get there. So I'll go ahead and erase all that, and we'll go to the next slide. So if you had cubic feet per second, let's say you wanted to get to gallons per day. So what path should we take to get there? So if you go back and look at the way that we could get there, the path is several ways. Like we could go this way and across, we could go this way and down, we go this way and across. There's all these different ways that we could arrive at the gallons per day if we wanted to. So let's try that out real quick. Let's try this out. Now over here, just a second ago, I said this was 86,400 cubic feet per day because we started off with 1 cubic foot per second. We multiplied the 1 times 60 to get 60 cubic feet per minute. And then we multiply by 1440 to arrive at the 86,400. And now what if I want this to be in pounds of water per day? So I use my 7.48. That was my factor of gallons of water in 1 cubic foot. So I'll make sure I'm telling you the right things here. So 86,400 cubic feet in a day, multiply times 7.48 gallons per cubic foot times 7.48. Now all of a sudden I come up with a number that looks like this. I have 646,272 gallons per day. That's a lot of number. That's a lot of water gallons per day. It's a large number, but that's not the only path that you could take to get there. So for instance, I could go this direction. I could take the 1 and multiply by 7.48 and go this direction. So now I would have 7.48 gallons per second if I took that path. And now 7.48 times 60. So 7.48 times 60. And I get 448.8. So now I'm over here now at 448.8 gallons per minute. So I converted cubic feet to gallons per second and then into gallons per minute. So now if I want to get this into gallons per day, I would multiply the 448.8 multiply times 1440 minutes in a day. And I come up with, guess what I got? I got 646,272. So I came up with the same number. So like I said, there's multiple ways that you can take the paths to get to the same answer. And I'm not here to tell you you have to do it any one specific way. I just kind of want to show you a way to get to a successful, correct answer. You're certainly welcome to take other paths. So. All right, the next thing we want to discuss is how do we convert inches into feet? I kind of alluded to this a little bit earlier. I said that we have to be cognizant of the fact that we're going to have something as inches, and we may need that to be in feet units. So most of the calculations that we're doing here today are going to involve feet. One of the reasons we do that is because we know that 1 cubic foot of volume, 1 cubic foot equals 7.48 gals, right? Gallons. So we're working with feet units. You can kind of see right there, it's cubic feet units. We're not really going to be working with cubic inch units in any of this math. We want everything to be in cubic feet units. So, or feet units, depending on what we're working on. But it's really common in the water distribution system operation and the field. It's really common for us to say we have this pipe is an 8-inch pipe, or that pipe is 6-inch diameter, or we have, we need a wraparound clamp for a 12-inch pipe, that kind of thing. So it's really common for us to use inches in our words, but the math usually requires us to be in feet units. So just want to kind of point that out to you and make sure that you recognize that. So when you come up with a number of inches, what we need to do is take that number. Let's say we have 8-inch pipe. So we have an 8-inch diameter pipe. We're going to say inside diameter. I'll put over here ID equals, so inside diameter equals 8 inches. And we're going to divide that by the number 12 inches per foot. So that's going to be our conversion. So now our inside diameter is no longer 8 inches. It's going to be a portion of a foot. So we're going to say 8 divided by 12 is, on my calculator, I got 0.6666666, and it just keeps right on going. So how far out should we go with this? And what about all these sixes, and how do we round that? For purposes of most of the math we're going to do here, we're going to go out to, let's say, the second decimal number, or the second number after the decimal to the right, and we'll just drop off the other numbers. So this would actually be rounded to something like this. 0.67 would be the feet units that we're going to use for a calculation. So I'm going to go out to usually the second decimal number over, and we're going to round basically using the rounding function of if a number to the immediate right of another number is 5 or higher, which in this case, this number 6 right here is higher than a 5, then when we drop that 6 away, this actually became 0.67. That 6 went up 1 digit. So that's how we do the rounding. If it's 4 or less than, or any number less than 5, we round down. So it would just have stayed 0.66 if that was the case. So anyway, that's how we're going to do this math with converting inches into feet. So here's some examples. We have a water main that's 6 inches in diameter. So I'm going to write it up over here. I'm going to say 6 inches divided by 12 inches per foot. And I'm going to write the first one out so you can kind of see it. So 6 divided by 12, I get an answer of 0.5 feet. So hopefully you guys can see how that came out on my calculator, and that you see a corresponding number. Many people say that, well, I know that 6 inches is half a foot, so I'm just going to say, well, then it's 0.6. Well, that would be incorrect. It's not actually 0.6, it's 0.5. A half of something is considered 0.5, in this case, or 0.5. So that would be the correct answer for a 6-inch water main. Convert 2 inches into feet. So we're simply going to go 2 inches, divide by 12 inches. And let's see, we get 2 divided by 12. I got 0.166666, and it keeps right on going. So I said I was going to do the rounding where I only keep 2 of the digits after the decimal point. So I'm not going to use 0.166666. I'm going to say that this is going to be 0.17. So I'm going to drop off all those 6s. So that number next to it, that 6 there is going to round up to a 7. So 0.17 feet. And by the way, since we're just kind of working on some basic calculations here, we will be accurate enough for what we're needing to do in our calculations in the field or on an exam. You'll be close enough to any answers. Now, if you said you wanted to be extremely accurate and you needed to have exact numbers for some reason or other, then by all means, keep all the digits in place if you'd like to. You don't have to round off the way I'm showing you. You certainly could round a little differently. Just wanted to kind of point out that the way I'm doing it, you will come up with answers very close to any questions or any possible choices on an exam situation, or in the field, you will be able to come up with a number very close enough to accurately dose a chemical, or to size up pieces of equipment or fittings, things like that. The next question, it says a pipe has an inside diameter of 16 inches. So the formula is written out like this: 16 inches. It's exactly the same way we've been doing the other ones. So it's still 16 divided by 12. And I come up with 1.33333. And like I said, we don't need to keep all those digits. So what we can just do is say, okay, I'm not going to use 1.333. I'm just going to put 1.33. And you'll be accurate enough. So we don't round up to 1.34 because the other digits are 3 as well. So 1.33. And what about this last one? We have a water main that has 54 inches. It says a 54-inch water main equals X feet, X number of feet. So to write this one out the way this is asking us, we would say that X equals, right? That's kind of using little algebraic terms there. So it's the same formula. X equals 54 inches divided by 12 inches per foot. So then X is going to be what? So 54 divided by 12 inches, I get 4.5 feet. So X equals 4.5. So that's how we do that. That's how we do the conversion from inches into feet. Pay attention to that. You will need to know this, and it will be very important to us in some of these calculations. All right, let's see. I went backwards here. I should have gone forwards. All right, so that actually ends the introductory part of this, and we're going to get into part 1 here shortly. I'm going to take a quick break, get another cup of coffee, and kind of wet my mouth a little bit here. I'm talking all day, so I hope that you guys might take a little break, and I'm going to pause the recording, and I'll be back here shortly. So I'll see you back in just a few minutes. Okay, everybody, welcome back. We're going to get into part 1 of 7 of our water distribution system mathematics. This section is going to be covering what we call geometry review, which is going to be the shapes, the sizes of circles, rectangles, cylinders. We're going to be working area, volume, and circumference, and I'll describe what those mean to us as we go through. So you're going to see some of this out in the field. Obviously, you're going to need to know this for different purposes of working with the distribution system, and we're going to need to know this for calculating things that will be on your exams. So let's go into it. First is the discussion of how do we show the units of measurement with things like area and volume. So area is known as square footage. Area is similar to if you're going to, let's say, paint a wall of your house, and you need to know the flat surface area. You need to know the area in square feet. And generally, most of our units of measurement here in water distribution system math are going to be area as square feet. So I sometimes write it out on the formulas, or in my results, I show feet with a 2 exponent next to it. So what that really means is some kind of feet times a feet unit is going to be there. So it's 2 foot units multiplied together. So that's what that exponent 2 means. Or sometimes you'll see it written out with abbreviations like that, like SQ for square and FT for feet, or just square feet written. So either way, it's the flat surface area. Volume then is the like a 3-dimensional shape or a 3-dimensional view, and think about like what's inside, like there's a place inside, a space inside of something. So it's more of a 3-dimensional shape. And so we generally abbreviate this as cubic feet, or abbreviate cubic and feet like you see here, or with the exponents involved, we have feet with a 3-digit, which means it's dimensions of 3 being multiplied together. So it'd be something with feet times feet times feet, or multiplied by by there. So feet times feet times feet, and like say length times width times height would be in feet units. So that would be an exponent of 3, which is what you see written here. So feet with a 3 exponent. So it's the volume inside of a tank or the pipe, the empty space inside. So let's take a look at some of these. So flat surface area, squares, rectangles, it's simply the length and the width, or width and length, however you want to describe it, for a flat surface area of a square, a rectangle with a circular shape like you see down here. It's the distance across from the perimeter to perimeter, which is known as diameter, and then halfway across, if you're only going from halfway across, say, to the perimeter, that's known as radius, and I'll describe that in just a second here. But anyway, a circular shape or a square, rectangle, is all square feet. There's essentially 2 foot units that are used in the calculation. That's what gives us the square feet. So let's take a look at a square or rectangular shape first. The reason we know the question would not be something like a round shape is because we don't have the word diameter or radius in it. The word diameter and the word radius would kind of lead us to the path that is a circular shape. So this question says, and we're using the formula shown here in the red arrow, the question reads, how many square feet of sod will be needed to replace the grass after a main break repair? The length is 36 feet and the width is 8 feet. So we have a 36 foot long area that we've got it all graded, and we're getting ready to put some sod down. And remember that area is equal to 2 foot units, length times width. And by the way, these would be in feet. So we're going to come up with feet squared. So simple calculation at this point. Hopefully you're kind of see that we would take the 36 feet and multiply that by 8 feet. And on my calculator, 36 times 8, I came up with 288 feet squared. Or you can write it like this, square feet, either way. So 288 square feet. So you call up the supplier of the sod and you say, hey, I got to cover 288 square feet and send me whatever you need, whatever method that the shapes that you have. If it's in a roll, and we'll just roll out, I need to cover at least 288 square feet. So that's how we do the area of a flat surface, either rectangle or square shape. The circular shapes get a little bit, a little bit tricky. So we're kind of still talking square feet, but now we're dealing with a circular shape. So it's kind of a little confusing to some folks, but let's see how this works out. So we have the arrow pointing to the calculation we're going to use. Is circle for square feet of a circle is area times 3.14, which is known as pi, the symbol called pi. And for our calculations, we substitute the symbol that looks like this. Pi is a symbol that looks like that. We're going to substitute that symbol for the number 3.14. So on the first formula that's shown for it, we have 3.14 multiplied by the radius that's squared to itself. So remember, when we see exponents, that we have to do that first, or in parentheses, actually anything parentheses first, but exponents would be second. So whenever you square something, let's say we're going to do a calculation like this circular shape, and we say radius with a 2 next to it, or radius squared, it's simply radius times radius. So whatever that is, whatever that radius number is. So radius is 10 feet, it's 10 times 10, or 6 foot radius would be 6 times 6. So we're just multiplying it by itself. When we square something, it's just that number times itself. So the formula would be like this: 3.14 times radius. And those radius numbers would be in feet units, and then we would have our square footage. But there's actually 2 formulas. There's 2 ways to do this. And I told you that I'll try to only show you one way, but I will show you this because many times we're trained and taught as adults to use 3.14 or the second one, which is 0.785. So I'll be kind of working both of these out as we go through the math together. You'll see that you'll come up with the same exact answer, by the way. You will come up with the same number no matter what way you do it. Just make sure you put the numbers in correctly into the calculation, so you're not mixing things up like diameter and radius and all that. So the formula could also be, as you see, as a secondary choice, it says or. 0.785 times d squared. Now, remember, d is going to stand for diameter. So in this case, it'll be diameter times diameter by its, multiplied by itself. So let's remove that little 2 there, and let's go like this. Let's go d times d, and that would be the formula. So it would be the number 0.785, which is a constant, times diameter. So that's how we would do it. So let's take a look. We have an example. So just use one of them consistently. I would say, I would tell you that most people tend to gravitate towards one or the other, and they stick with that. And that's just fine by me, whichever one works best for you. So diameter is shown here by the purple colored circle, and we have a line all the way across the center of the circle. So from perimeter edge to perimeter edge, all the way across the center is known as diameter. And the radius is half of that distance. So if we were to say start our arrow here in the center and then work over to the edge, then we would have what's known as the radius. So it's half of the diameter. It's more common in the industry, I think, just so you guys know that it's more common for us to describe pipes and things, that we use in the field with the word diameter than it is with radius. I would say most people say, hey, I'm working on an 8-inch pipe. Well, the 8-inch pipe really means the inside diameter as radius. Or if somebody says, I'm going to need some fittings for a 3/4 inch pipe. So 3/4 inch is the diameter across the middle. So just kind of get used to that. Not too many people use the word radius, but you could see it like on a quiz question. So we got to pay attention to what form is actually shown to us. So let's work this one out. So what is the cross-sectional area? Now the word cross-sectional area just means like if you cut a piece of pipe and there's this circular shape in front of you, that's the cross-sectional area. So what is the cross-sectional area of a pipe that is 1 foot in diameter? So you have a couple choices here. Remember I said you have 2 methods of doing this. And by the way, right now our units are in feet units, so we don't have to do any conversion of inches into feet. So I'm just going to write out the formula either way. So I have 3.14 times the radius. So what is half? If the diameter is 1 foot, what would the radius be then? We need that radius to be half of 1 foot. So how do we calculate half of 1 foot? So we would take 1 and divide that by 2, because there's 2 halves in a whole. So the number 2, so 1 divided by 2 is 0.5. So essentially for the 3.14 method, we would need to convert this 1 foot into radius, because the 1 foot's diameter, we need the radius to be 0.5 feet is the radius. I'm just going to write that up here. Radius equals 0.5 feet. Diameter is 1 foot. So to use the 3.14, we need the radius. So let's go ahead and use that. So we erase that, and we're going to go 3.14 times 0.5 times 0.5, which is a half a foot. These are feet units. So let's work this out on our calculator. 3.14 times 0.5 times 0.5, and I get 0.785 feet. Now this is feet squared because we're working with area. So the opening of that pipe, 1 foot in diameter, is 0.785 feet. All right, so now if we're going to use a formula like the shown here, if we're going to use a secondary formula, the formula will be written like this. It'll be 0.785 times the diameter. The diameter was how many feet? We said the diameter was 1 foot. So times 1 foot times 1 foot. So on your calculator, you take 0.785 times 1 foot, and I get, guess what? I get 0.785 feet squared. Remember, there's 2 units there that have foot units next to it, so it's square feet. So 0.785 square feet for either one is the opening of a 12-inch diameter pipe. where's the 0.785 come from, initially? How does this work into the calculation? Let me kind of explain a little bit. Maybe this will help clarify it. If you were to have a square shape, if you drew a square shape, which is coming up on my next slide, if you were to imagine a square shape that was 2 feet across by 2 feet in height, or width as 2 feet and length as 2 feet, however you want to word that. So we have a 2 foot by 2 foot square. If we were to draw a circle directly inside that square, so it takes up, from edge to edge to edge, the circle would fit inside, but the edges of the square would not be inside of that little circle. They would be left out. So we would need, if we calculate the area of each of these shapes, you'll see that the circular shape inside the square takes up or consumes 78.5% of the total area of that square. And so when we write the number 78.5, when we write that as a decimal, we actually move the decimal point 2 places when we convert from percentages to decimal point numbers, and the number becomes 0.785. So let me show you how this works out. We've got this circular or square shape here. So we've got 2 feet by 2 feet. You can kind of see that a square box or a piece of plywood, is 2 feet by 2 feet. So we're going to figure out the area of the square. Remember, it's length times width. And now since they're the same number, it's just going to be 2 times 2, and I'm getting 4 square feet. And you can kind of see here, we've got 4 squares showing, which would be 4 square feet in one, in this whole box or this square. But what would the area of the circle be if we were to put a circle inside this? So here's our circular shape. Now, remember, the area of a circle is 3.14 times radius, or 0.785 times D. Remember, that's how we do the area of a circle. So if we did the 0.785 method, which is, we have diameter right here. Diameter is actually all the way across. We have 2 foot diameter. We would say 0.785 times 2 feet times 2 feet. And let's see what we get. So 0.785 times 2 times 2, and I get 3.14 square feet. So my circular shape inside that square is 3.14 square feet. You'll notice that the little edges around here are not encompassed inside of that circular shape. You can kind of see that they're left out. So then if we take it to the next step and say, well, how much percent of that square box is covered by that circular shape? What's the percentage? We would say that the percent is, how do we figure 78.5? How did we figure that out? How do we figure 78.5? I just showed you an answer there. So to figure 78.5, we would take the circular shape square feet is 3.14 square feet of the circle and divide it by 4 total square feet of the square box. So 3.14 divided by 4 gives me an answer of 0.785. So there's a decimal equivalent of the answer. That's the difference between the two shapes. 0.785 as a decimal. And if we want this to be as a percent, we multiply it by the number 100, which actually moves the decimal point to the right 2 places. So 0.785 times 100. And guess what I got? I got 78.5% of the circle of the shape of the whole square. 78.5% of that square shape is covered by the circular shape. So that's how we work that out. So not the whole square is covered by the circle. And that's kind of how that 0.785 works out. That's where that really comes from. So I don't know if that's a mystery that you wanted to be solved or you don't really care or not, but I thought it was kind of helpful to kind of let you know that, hey, that's where it comes from. if you just use one or the other, just follow the math the way it's shown. You can certainly work it out. If you do 3.14, the radius would be 1 foot. So 3.14 times 1 times 1 would come out similarly to 3.14 square feet. So that's pretty interesting. That's kind of where that all comes from. So the area percent area covered is 78.5, and we write that as a decimal as 0.785. So anytime you see a percentage, so 78.5 is written out as a percentage on that one statement. Anytime we have to get it into a decimal, we divide by 100, which is percent as a decimal, or written per whole. So 100% for the whole. So 78.5 divided by 100, and we have a decimal equivalent of 0.785. You can kind of see it put a decimal or move the decimal this direction 2 places over to the left. So just kind of remember that anytime you see a percentage, you need it as a decimal, just divide by 100 and you'll have it as a decimal equivalent. There you go. That's it. So let's try one out here. So we have an 18-inch diameter pipe. It's 20 feet long. Calculate the cross-sectional area of the pipe as square feet. And I'm asking you to try both formulas, try them both out. So I'll write them out on the screen here, and hopefully you'll be able to follow along. And the first thing I'm going to do is recognize that the question is asking me square feet as my answer units, but my diameter is given to me as 18 inches. So I need to convert those 18 inches into feet units first so I can work the math. So remember how to do that. It would be 18 inches, divide that by 12 inches in a foot. So an 18-inch pipe divided by 12 is actually 1.5 feet in diameter. So 1.5 feet in diameter is the same as 18 inches in diameter. So all we're going to do now is use the foot units instead of the inch units. So let's work this out. So we've got, since we've given you diameter, many people say, well, I'm just going to use the 0.785 method because diameter was given to me. So 0.785 multiplied by 1.5 feet by 1.5 feet. And what is my cross-sectional area of the pipe? So 0.785 times 1.5 times 1.5. So I've got on my calculator 1.76625. And like I said earlier, we don't have to keep all of these digits for our mathematics. We can round that off, drop some of those numbers. And if we go with 1.77 feet, that will be just fine. So essentially the 625 goes away and we end up with 1.77 feet. That's the one method. What about the 3.14 method? So 3.14 multiplied by what? Now the question gave me the question gave me diameter, and I need it to be in radius because remember 3.14 goes with the R. So we need this diameter actually to be cut in half. We can't use the 1.5. So how do we convert 1.5 into halves? So 1.5, divide that by the number 2. So when we divide 1.5, we actually break it into 2 halves, and each half then is 0.75 feet. So 3.14 times 0.75 feet for the radius times 0.75 feet for the radius now gives me what? So 3.14 times 0.75 times 0.75. And I've got, guess what? I got 1.76625. Or you can just say 1.77 feet and we're good to go. So either way, you come up with the same answer. So try it out, work in both formulas, should get familiar with it. If you'd like to pick one that works for you, then kind of, build your strategy around that and say, well, if everything's given to me in diameter, I'm going to go with 0.785. Or if I choose radius, I have to watch out that if diameter is given to me, I need to convert it into the radius. If you actually work the math incorrectly, let's say you put the 3.14 with the diameter times diameter, you will get an incorrect answer. And there may be a possibility that that potential answer that you got could be a fake answer or an incorrect answer or distractor, they call that, on an exam or a quiz, multiple choice quiz. So just watch out for that. So many of you might be wondering, how come we had to cut the diameter in half and then square it to use the 3.14? Why couldn't we just use the diameter as its own number and just go with that? Well, the difference here is what we're trying to do with area of a pipe is the cross-sectional area, like the flat surface, so to speak, of a pipe or a circular shape is what we're trying to work with. And the units of square feet come from the fact that we're squaring numbers times themselves. If we didn't square the number and we just put the diameter in by itself, it actually would not give us the correct units or the correct value that we're looking for. In fact, if you did do what I just mentioned, just use the 3.14 times the diameter number, you actually get something known as the circumference, or the distance around the pipe. The outside dimension is really what you're going to get. So circumference is the distance or the linear feet around a shape. And that's a little bit different. So it's a different calculation. So the formula looks like what you see here on the screen. You see where it says circumference is known as linear feet. Linear feet just means the line distance. If we drew a line, how many feet is that line going to be? It's a one-dimensional shape. It's not two-dimensional. It's not three-dimensional. It's a one-dimensional shape. So linear feet is just how many feet of distance. Circumference is known as perimeter, and perimeter is kind of more commonly used with a shape like a rectangle or a square, where circumference is more commonly used with circular shapes. So I'll describe those here as we go through this. So perimeter commonly with square, and circumference is commonly with pipes and circular tanks and things like that. So here's an example using the rectangular part of circumference, also known as perimeter. So the question reads like this: what is the perimeter of this rectangle if the length is 180 feet and the width is 65 feet? So imagine, if you will, you have a piece of land and you want to put a fence around that piece of land because you have a water plant or a well or something like that, that you want to kind of keep fenced in and keep protected or whatever. So the perimeter, what's the perimeter of the rectangle if the length is 180 feet and the width is 65 feet? So there's a couple ways you can do this math. Remember that you could just add them together, and remember that there's two distances that are 180 feet. This is 180 feet here, and this is 180 feet here. Put 180 here. These are feet units, and the width is 60. What did we say? 65 feet here, 65, and this distance here is 65. So the formula could be where you just add all four of them together. That would give you the perimeter all the way around. The other way you could do it is what they're showing here on the screen in front of you. The formula is written like this. It has the number 2 times the length. Notice that's in parentheses. And then it has 2 times the width, which is also in parentheses. So you would actually do those multiplication numbers first and then add the 2 together. So either way will give you the same answer. Let's try it out the way the formula shows. So we have the number 2 times the length, which we said was 180. So 2 times 180 feet gives me how many feet? So 2 times 180, I get 360 feet. That would essentially be the same as if you just added 180 and 180 together. It'd be 360 feet. The second part of the formula, so this would be written like this. The second part of the formula is where we have 2 times the width, and the width we said was 65 feet. So 2 times 65. Actually, let me erase something here because I put my parentheses in the wrong spot. Let me just erase that and go back to this. So 2 times 65 equals what? 2 times 65, I get 130 feet. So we're going to add together 360 feet plus 130 feet, and the total feet, 360 plus 130, the total feet I got is 490 linear feet. It's the distance all the way around. So if you were to walk that whole distance, you would walk 490 feet. So that's how we do. It's kind of more commonly called perimeter. So fence is bought in linear feet. You're going to, how many linear feet of fencing do you want to buy to protect a water treatment plant or a well house or your yard where you have all your pipes and pumps and parts and fittings and trucks and all that. So usually they're fenced in to kind of keep everything secure. So you would need 490 linear feet of fencing material. But what if the shape was a circular tank and you had to, let's say, estimate the amount of feet all the way around the tank? Let's say you were, in charge of landscaping, and somebody said, "Well, I want you to take this weed whacker and weed whack all the way around this tank." So that's your job is groundskeeping for the day, and now you want to know how many feet you're going to walk when you walk all the way around the perimeter of that tank. So the question would be, it says a ground storage tank has an outside diameter of 98 feet. So the diameter across the whole tank, from the outside edge to outside edge, is 98 feet. What is the circumference of the tank? So my formula shows what you see up here. It says circular shape equals 3.14 multiplied by D. And D in this case is 98 feet, and that's the diameter. So we're just multiplying those two together. So 3.14 times 98, and on my calculator I got 307.72, and that is feet. So 307.72 linear feet of distance you would have walked. So that's how you do circumference. All right, so hopefully so far so good. But it does get a little trickier, because with water distribution systems, we don't just use or see ground storage tanks. We also see things like pipes. So here's where this gets a little bit more critical, maybe, as an example goes. So we're going to use a wraparound clamp to fix a water main leak, and we want to use this clamp in it, and the clamps are generally given to us in a range of inches, and the inches are the length is in inches, and it's a range between some number and some other number, and the range is because of the length of the threads on those bolts. So we could actually fit a different range of pipe with a wraparound clamp. So let's just say, for instance, in this case, we have a water main, and you've measured that the outside diameter. So you got a water main. Let's say we've got a water main leak, and we have to repair it. So here's a water pipe, and the outside diameter is 10.8 inches. Okay, so the diameter across. Now, in this case, because the units of measurement we're looking for are in inches, as an end result, we can just use the inches that we have. We don't have to convert this into feet. And how we know this is because answers for questions like this would be in inches. So in this particular case, we're using a clamp, and we want to know how many inches around the distance is. So what's the circumference? So we're going to use 3.14 and multiply that by the inches in diameter. I got 10.8. And so for my outside diameter circumference, I have 33.912 inches of circumference. So you're going to go to the shop and look for a wraparound clamp that would cover the range somewhere that would cover this 33.9 inches of shape. So hopefully that helps you guys out a little bit. So sometimes they're directly given as the diameter equivalent, or as total inches that it would cover. So All right, so here we have another one. A 6-inch ductile iron water main has an outside diameter of 6 7/8 inches. What is the circumference of the pipe? So this is a tricky one because we have a couple of numbers showing here. It says a 6-inch ductile iron main. So we generally say, oh yeah, this piece of water pipe is 6-inch ductile iron. Well, that's the inside diameter, the nominal inside diameter length across from edge to edge. But the outside diameter is 6 7/8 inches. What would be the circumference of the pipe using this? So here's what we have to do with this. We really need this fraction right here. This fraction is going to give us a little bit of trouble. We need that fraction to be as a decimal number, not as a fraction. We can't put the fraction in the calculator very easily. We actually need that to be in a decimal equivalent. So what we're going to do is we're going to, for this purpose, we're just going to put this 6 inches off to the side just for a second. And we're going to remember that that's a whole number. But what about this 7/8? So here's how we do this. We take the number 7, divide it by 8, because a fraction is actually 7 into 8. So 7 divided by 8. So 7 divided by 8 is equivalent. This is going to be an equivalent of 0.875 inches. So 7/8 of an inch in a fraction is actually 0.875 inches. So less than a whole inch. So it's 0.875 inches. So then we remember here that we have a 6 here. We had 6 whole inches. So we're just going to add that back into the 6 inches. And now we have a number that looks like this, 6.875. So we have total inches now of 6.875 inches. And now we do our circumference the same way. So 3.14 multiplied by 6.875 inches. And let's see what we get. 3.14 times 6.875. And I now have a outside diameter, or I'm sorry, outside linear feet in inches is 21.5875 linear inches. I misspoke there a second. I said linear feet, but this is actually linear inches. This is the inches all the way around this pipe. If you come back around, it would be 21.5875 inches, or rounded up would be 21.59 inches. So that's how we do it. Linear inches. That's the distance in a line. All right. So I hope that helps you guys out. This will be important in a little while. You're going to see us talk about this circumference, and we're going to need to know this because when we start putting paint on this, when we start painting this pipe, to prevent corrosion and all that, and to protect the pipe, we're going to need to know the circumference, and that's going to be important. So we'll get back to that again in a little while. Let's move on to feet, or I'm sorry, cubic feet. Let's look at volume as cubic feet instead of just flat surface areas. Let's look at the 3-dimensional shapes. So a square or rectangle would have 3 dimensions in it, and it would be known as cubic feet. So it's kind of the space inside this box. A circular shape is really no different. It's the cubic feet of volume down inside that tank, or what's inside the pipe, or maybe how much air is inside the pipe, cubic feet of air inside the cubic, or the tank itself, or whatever. Even though it's a cylinder, it's still referred to as cubic feet. So for cubic feet, we write it out like this. I generally put feet with a 3 exponent, which means feet cubed, because there's 3 dimensions. It's a 3-dimensional shape. So we have length here, we have width here, and we have height here. So length times width times height, 3 dimensions, and we get feet cubed. Circular tanks, it's the same as before. We have 0.785 times D times D, which gave us the square footage. And now we have the height, which is the 3rd foot unit in there. So it ends up being feet cubed. So let's look at some examples. Here's our formula for the volume of a cubic feet. And again, this is on your formula sheets. and the volume is equal to length times width times height. Just make sure the units are all the same. If we start working with inches in one thing and feet in another, we're going to come up with some erroneous number, and just watch out for that. Common question to see on a quiz is things like how many cubic yard or cubic feet of soil are removed, or how many cubic feet of concrete are needed, or whatever. So we have to make sure all our units are in the right order with each other. So they're equivalent with each other, feet and feet and feet, or inches, 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 depending on what you're working with. Just make sure they're all the same. So here's a good example. We have a question that says, how many cubic feet are found inside a water meter vault? That is 10 feet long. So we're working volume here. So volume is length times width times height. So we have 10 feet in length. We have 8 feet in width, and multiply that by the depth. In this case, instead of the word height, it says depth. So we're going to go 6 feet as depth, and we're going to multiply those three together. So I got 10 times 8 times 6, and I have on my calculator 480 cubic feet as the volume of that meter vault. So that's how we would work that one out. Length times width times height, the three dimensions together gives us cubed feet. Let's talk about the cylinders now. The cylinders, again, kind of throw us off a little bit because it's a cylindrical shape rather than a square or rectangle, and we're still using some of these same formulas to help us out. So cylinder or cylindrical shape is going to be either, you have two choices here. You have volume is equal to 3.14 times the radius squared times the height, or you can use 0.785 times diameter squared times the height. Remember, either one of these would come up with the correct answer. So here we have a question. It says, calculate the volume of a ground storage tank that is 80 foot in diameter and 18 feet tall. So we have the possibility here, because the word diameter is in there, we know that it's a circular shape. So if we go directly to the 0.785, because it involves the diameter, we would write it like this: 0.785 multiplied by the diameter, which we said was 80 feet. And we're squaring that first by multiplying it by itself. And then the third dimension is the 18 feet. That is the height. So we're going to multiply those numbers together. If you're a fan of the 3.14 method, which is pi, and we multiply by the radius. Remember, radius is half of the diameter. So what is half of 80 feet? So half of 80 would be like this: 80 feet divided by 2. We're dividing it into 2 halves, and we get 40 feet. So to work the 3.14 method, it would be 3.14 times 40 feet times 40 feet. And then again, my height units needs to be used. So I got 18 feet high, and either one of these should come up with the same answer. So 3.14 times 40 times 40 times 18. And I got, on my calculator, I got 90,432, and my units now are feet cubed. So feet cubed, cubic feet. There we go. So that's how we work that one out. So that's the volume of a storage tank. A pipeline. We also have to know how to do a pipeline, because cubic feet is not just in storage tanks or large things, it's in littler shapes too, or smaller shapes. So this one says, calculate the cubic foot volume inside a 12-inch water main that is 1,500 feet long. So we've got this really long water main that's 1,500 feet, and we want to know how many cubic feet of volume are inside of it. And it's a 12-inch diameter water main. So we're saying a 12-inch water main, that is going to be the diameter. Remember, I mentioned a little bit earlier, we typically go with diameter as a rule. It doesn't say anything about radius, so we're just going to use that's diameter. So first off, the inches units have to go. We can't use the inches. Remember, to convert inches to feet is the division of 12 inches divided by how many inches are in foot. which we said was 12 inches per foot. Divide 12 by 12, we get 1 foot. So a 12-inch water main is essentially a 1-foot water main. So working the formula, then we would have 0.785 times 1 foot multiplied by 1 foot, and then multiplied by the length is 1,500 feet. Now remember, length in this case is because the pipe's in the ground. It's would be equivalent if the pipe was standing upright and it was a storage tank that was standing upright. We call it a standpipe if it was 1,500 feet high. So length is equivalent to the height in this case. So 1,500 is the total linear distance. So what would that number be then? So we have 0.785 times 1 times 1 comes to 0.785 times 1,500 feet long. And I have 1,177.5 cubic feet of volume in this case. If you want to see the pi r squared method, it's 3.14 times the radius. Now we need half of the diameter. Half of 1 or half of 1 foot is 0.5. We already said that 1 foot divided by 2, because we're breaking it into halves, is 0.5. So 0.5 feet times 0.5 feet. Now remember, that is actually the radius. And we still need the 1,500 feet in there. So 1,500 feet gives me my formula. So 3.14 times 0.5 times 0.5 times 1,500. And I got, guess what? I got the same number, 1,177.5 cubic feet. Same number. Either way you want to do it, fine by me. I don't care, as long as you get the right answer. So, or the same answer. All right, so we've got volume taken care of. We've covered circumference, which is linear feet around something. We've got area, which is the cross-sectional opening and of a pipe, or if it's area of a rectangular or square shape, it's the flat surface area. So let's convert these things that we just talked about. Let's start converting these into gallons. So we are going to need that conversion factor. We're going to need the conversion factor of 7.48 gal per cubic foot. Now we already did the cubic feet. We worked that out together. Now we have to multiply by 7.48. So let's start practice with that. So gallons in a square or rectangular tank. The question on the table now reads, calculate the volume as cubic feet and then multiply it by 7.48 gallons per cubic foot. So it's just, in case you're wondering, it is actually just one long string of multiplication. You could even go like this, 0.7 or 7.48, sorry, here, which is gal per cubic foot. And you would then just multiply, oops, sorry, I'm getting a little sloppy here, multiply all those numbers together and you would get cubic feet. So it's just multiplying that extra number on there. So here's a word problem. The word problem reads like this: how many gallons does the water plant filter contain if the filter is 50 feet long, 20 feet wide, and 15 feet high? The water depth is 11.5 feet. So if you're taking a water distribution system exam or quiz and you say, well, why are they all of a sudden asking me about a filter? Because I'm not working with filters. Well, here's the thing. Try not to get all worked up on what the unit is or what the description is of the shape. It really doesn't matter that it's a water plant filter. That is just extra information. Think about it as a shape. Think about it as a three-dimensional shape. The length is 50 feet long. So we have a 50-foot long shape. We have a 20-foot wide width to this shape. And the height is 15 feet high, right? And that's the height. And they gave us an extra piece of information. It says the water depth is 11.5 feet, which means the height of the water in the filter is 11.5 feet. So this is where we have to kind of pay attention. What are we trying to figure out? We're trying to figure out how much water in gallons is inside the tank, not the total volume of like the water and the empty space in the tank. We really need to know the water gallons, and the water height is important in this case. The water height is 11.5 feet. So that number is actually what we need to use for this, not the total 15-foot height. We don't really care about the empty space above the water. We want to know what the water height is. So I need to erase something here. And I'm going to erase this number because this is actually the wrong number to use for this. And maybe you already caught that as we were talking about this. So the height of the water is used. We have 11.5 feet. And now we know the cubic feet of the actual water inside. So let's figure out what that is first. Let's do the cubic feet. So it's 50 feet long by 20 feet wide times 11.5 feet. And my cubic foot volume of just the water is 11,500 feet cubed. So that's my cubic feet. That's not the finished answer yet. That's just cubed feet. What the question's asking us is how many gallons would be in that filter. So we're not quite done yet. We have to now convert into the gallon units. So we're going to take 11,500 feet cubed. And remember, our multiplication factor is 7.48 gal per cubic foot. And let's multiply that. So it's 11,500 times 7.48. And my answer now is 86,020 gallons. There you go. So that's the final answer. This is the final number that we're looking for. So we have 86,020 total gallons in that filter. We don't care about the whole height of the filter. We just need the elevation of the water. So pay attention to that. That's a similar type of situation in water storage tanks, elevated storage tanks, things like that. So you want to pay attention to the numbers that are given. It is common to see sometimes extra information given in word problems. And so you want to just pay attention to what really is happening. In some cases, it's not a bad idea even just to draw out like a little picture if it helps you kind of, imagine what this is. I just draw a little picture here, kind of draw a three-dimensional shape. And so we have this filter and it's 50 feet long. We said it was 20 feet wide here. And the total height of the filter was 15 feet right here. These are all feet units, but the water is only up to 11.5 feet. So if I kind of go like this, say the water is here. This is the water elevation. That's the water inside the vessel or the filter, and the water distance was 11.5 feet. That's from here to here. That's the number we need. So just watch out for that and just pay attention to what units are given. If you're taking an exam or you're trying to practice for a quiz or something to that effect, we get nervous and we're working really fast and we're trying to hurry up because we have a limited amount of time. And sometimes we don't pay attention to things like I'm just showing you here. So sometimes a wrong answer is calculated for purposes of exam situations, and sometimes the factor of 15 feet is used and they come up with a wrong answer and they put that as one of the answer choices. So if you're not paying attention, you could actually pick an incorrect answer choice, and even though you know how to do the math, it's just we're going too fast. So just take your time. I've done that myself, even recording another video here for you guys to watch. In another avenue, I was recording water treatment and wastewater treatment math, and I was just cooking right along, and I'm doing all my calculations, and I'm saying to you guys, yeah, you got it, we're good. And all of a sudden I realized that I was not paying attention, and I did the same exact thing. So just know that we all do it. Just take your time, double check your work, make sure you know where you are with the math and what units you're at. All right, let's talk about the cylindrical tanks or pipelines. Let's talk about how we calculate the gallons in a cylinder. So we still do the same calculation that we did with volume. And in this case, we just multiply the 7.48 into the equation. So let's look at an example here. A water tank is 60 feet tall and 24 feet in diameter. How many gallons could this tank hold? Now, there's no extra information in here to say that, the water elevation is this or anything like that. So we're just going to use the numbers that are given as saying how many gallons could the tank hold if it was, filled up to 24-foot height. So let's use the formulas that we know that we have already talked about. Because we have diameter, I'm going to show you first the 0.785 because diameter is given. So 0.785 times 24 feet times 24 feet. That's the diameter times diameter, which is squared. And then now we multiply by the height. The height of the tank is 60 feet. And that's going to give me the cubic feet inside the tank. If you were working this math and you said, okay, yeah, but the question's asking me about gallons, you don't have to stop there. I'm just kind of doing this to show you as we work through the math what the units are. But if you're comfortable, you could just write it like this because we're trying to get gallons. It would be times 7.48 gal per cubic foot. So just multiply, just continue your multiplication. If you're using the pi r squared method, it's 3.14 times the radius. The radius is going to be half of the diameter and half of 24 feet. If I go up here into my word problem, divide 24 by 2 and you get 12. So the radius is 12 foot by 12 foot. And the height, again, is kept the same at 60 feet. And that's going to give me, my answer right now would be cubic feet. And you would then multiply that by 7.48, and you would get the final answer. So let's work this out. So 0.785 times 24 times 24 times 60 times 7.48. And if the tank is completely full of water, all the way up to the 60-foot height, I would have 202,929.408 gals in the tank. So 202,929.408 gallons could be stored in that tank. And if you want to check the math out, the other method, 3.14 times 12 times 12 times 60 times 7.48. And I got exactly the same number. I got that again when I did the 3.14 method. So double check your work, make sure you're paying attention to where you are. Just multiply it straight through and you're good to go. If you stop at the cubic feet and you don't remember to put the 7.48 in there, you'll come up with some answer. The answer would probably be something like 27,000, somewhere in that number range. And if that was an answer choice on the test, you might say, oh, well, I have it on my calculator. It must be 27,000. Well, that would be an incorrect answer. So if you came up with cubic feet, don't forget to convert it all the way into gallons. All right, what about inside of a pipe? So how many gallons would fit inside a pipe? And first off, why is this even important? So let me just kind of describe to you why this is important to you. The volume of water capacity that could be inside a pipe like this, or inside of a storage tank like I just showed you, the volume of water is important because we're going to be dosing chemicals into these shapes, and that's going to be for disinfection purposes for sake of a water distribution exam, or even for calculating, say, gallons per second of water moving. So we need to know the gallons for several different reasons. So let's talk about different pipelines. Let's talk about pipe shapes and stuff and how many gallons would be inside of a pipeline. Remember that a pipe is nothing different than a cylinder that's just laying on its horizontally rather than standing up like that picture I showed you that we worked on just a second ago. So we're going to need the length and we're going to need the diameter of the pipe so we can calculate the gallons inside the pipe. So here's our example. It says our example pipe has a diameter of 24 inches and is 20 feet long. So it's a 20-foot long stick of 24-inch ductile iron water main. So it says in the question, it says is made of ductile iron with a cement liner. Is that important to the math formula? No, this is not important to the math formula. We don't care. It could be anything. We don't really care what it is on that. All we need are the numbers, and we're going to figure out the gallons. So try not to get, oh, I don't deal with ductile iron pipes, so I don't know how to calculate it. Yeah, you know how to calculate it because you know the formula is. So the formula is pi r squared times d, or pi r squared times the length times the 7.48. That's the radius method. It's 0.785 times d times the length times 7.48. You do know the formula. So let's try this one out. So I just gave you some examples here. So if we're using diameter first, it's 0.785 multiplied by diameter. And this one says that the pipe is 24 inches. And I always just recommend to say, let's just knock this stuff out to begin with. Let's get rid of these inch units. Let's convert 24 inches of diameter into feet units. So there's 12 inches in a foot. So divide 24 by 12. And on my calculator, I got 2 feet. So my new diameter is 2 feet instead of saying 24 inches. So diameter is 2 times 2. Remember, we're squaring that. And the length we said was 20 feet long. And if we're trying to come up with gallons, why not just put 7.48 right here? And this is gal per cubic foot, because that's what we're going to calculate in this. So let's work it out. 0.785 times 2 times 2 times, we said 20 feet long times 7. And I just put 8.34 instead of 7.48. So 0.785 times 2 times 2 times 20 feet times 7. And I keep, for some reason or other, my brain is going a different direction. And 7.48. And so for gallons in this piece of pipe, I came up with 469.744 gallons. And if you want to try it out, the 3.14 method, I think that's where I was getting myself a little caught. So 3.14 method is pi r squared method. Now, we didn't give you the actual radius, we gave you the diameter, so you got to remember to convert into radius. So what is half of 2? 2 foot diameter divided by 2, because there's halves, 2 halves in a whole, is going to give us 2 divided by 2 gives me 1. So my radius then is 1 foot. So 3.14 times 1 foot times 1 foot times 20 feet in length. And we're trying to get gallons. So just put the 7.48 there, gal per cubic foot. And let's see what we get. 3.14 times 1 times 1 times 20 feet times 7.48. And guess what I got? I got the same number, 469.744 gallons. All right, there we go. That's how you're going to figure out the gallons in that pipe. Now, for purposes of disinfecting the pipe or purposes of just rounding either of these numbers, I would say, yeah, you'd probably be fine saying 470 gallons. All right, for purposes of what we're doing in the field, 470 would be just fine. So that's how we would do that. That's it. Let's try another one. Oh, by the way, there is a tutorial in the presentation that kind of tells us this. So I have a step-by-step tutorial in the next couple slides. So we divided the inches into feet. We came up with a 2 foot diameter, and then we kind of worked the math out. And remember, I said there was 2 ways of doing the math. So I kind of showed you here in the tutorial. So 3.14 method or the 0.785 method, either way gives you the cubic feet at this point. And then we're multiplying by the 7.48. is gallons, and there's our answer. So I would say, yeah, 470 is just fine. All right, how about this one? How many gallons are in an 8-inch water main that is 2 miles long? So here we have some units that are just completely outside where we need to be. So what we're going to do is start doing some housework up front. We got to convert and get things in the right units before we can use those formulas. So first off, the 8-inch water main is going to give us a little trouble. We need that to be in feet. And the word miles does not give us feet. That gives us a distance in, how many miles it is. So if it's 2 miles, we have to convert the 2 miles into the linear feet. So that's what we need to put into the calculation, not 2 miles. So this is a tricky one, and I would be prepared for this on any kind of quiz, or I think I've seen this in the American Water Works handbooks, any kind of water distribution system math. This is something that's really common that we would really need to know how to do, just like any of this other stuff. So let's work this one out. I got a tutorial here. The tutorial says that we're going to convert the 8-inch main into foot units first. Now, in this particular example, I went out to the 3 decimal points or 3 digits over. So instead of 0.67, I went 0.667. So again, no harm, no foul. You're still going to come up with a very close answer when we finish this math together. So now to do the volume of the pipe, we need 0.785 times 6.667 feet times 0.667 feet. That gives me square footage, right? That's the surface area of the pipe. And then we're going to multiply that by the length. Now, what's the length that we're dealing with? The length is 2 miles. So the first thing we really need to do is figure out how many feet are in 1 mile. So we can work it out like this. We have 5,280 feet in 1 mile. So on the conversion table, it actually says, I believe, 5,280 feet or 1 mile. So there's 2 of those mile units. So we rewrote the formula here. So here's our square footage opening of the pipe. And we know that 1 mile is 5,280 feet long. And there's 2 of those. So we multiply the number 2 into this. This will convert the miles into total feet. And now we just work out the math. Remember, now we're going to come up with the cube feet inside that pipe. So I'm going to double check this work here and see if they have the same thing I get. So 0.349, which is my square footage, times 5,280 feet for 1 mile. And we said there's 2 miles there. So I got 368 or 3,685.44. So 3,685.44 is what I've got. Looks like in this particular example, all we did was we said, we'll just round and lose the 0.44 off of it and just go with that many cubic feet. And again, you're going to be just fine with that calculation or that result. So I think we're pretty good on that one. That would be gallons in a water main. That's a really long water main, 2 miles long, and it's 8-inch in diameter. And if we want gallons, by the way, I'm sorry, I misspoke. That was the cubic feet. If we want it in gallons, we're not quite done yet. So we have the cubic feet showing here, which we just solved. And don't forget, there's 7.48 gallons in each cubic foot. So we weren't done. So multiply by 7.48, and I got 27,500. And I got, because I kept my number intact, a slightly different number. I got 27,567.09 gallons. Now, the only reason I got something a little different than what I'm showing on the screen here is because in my calculator, I had this number and I multiplied that by 7.48. If we had 3,685 directly, then you would have came up with this number. And either one is just fine. You see how close they are together. For purposes of what we're doing in water distribution operation, these numbers would be just fine. Either one of them is very, very close. So we're only off by a few gallons, and that's not going to make much of a difference when we come down to the actual calculation of, say, like disinfecting a pipe. So it's not a problem. So we should be good to go there. So gallons in a water main. That's it. If it was a 2-inch water main, you would just remember up here, it would be 2 inches instead of 8 inches. Same principle applies. All right, so now the next thing to cover is how do we convert these gallon units into what we need as million gallon units. The words or the units of million gallons are used when we calculate pounds of chemicals. The pound formula requires us to have the liquid volume in the units of million gallons, or if it's flowing water, that should be in million gallons per day rather than just say gallons per day. So the formula requires the right units. So what we're going to do here is describe how to convert those gallon units into mg or million gallon units. So how we do that is we take the gallon number that we calculated and we use a division. We divide that number by the number 1 million. And the 1 million is actually the units of this 1 million are 1 million gallons per mg, per million gallon units. We're breaking it into million gallon units essentially. So it puts a little decimal point in a place for us. And if we're doing everything right, the decimal point should be in the right spot. And then we have the right number to put into the pounds formula, which is coming up a little bit later. So here we have an example. We have an example showing of 657,400 gallons. How would we convert that into million gallon units? So I just mentioned to you that we would divide this number by 1 million. I'm put all the zeros in here, and 1 million is gal per mg. And so 657,400 divided by 1 million. And I came up with 0.6574 mg. So that would be the units as million gallons rather than gallon units. That's it. Many people have said, one thing that we're taught in school, a lot of people say, if you start off with, since this is a whole number, we would put a decimal point right here. And we would say from this decimal point here, we would move the decimal point 6 places to the left. And the reason we do 6 is because there's 6 zeros in the number 1 million. So whenever you go 6 decimal points over or move it 6 places over to the left, then that decimal point lands where it's supposed to be. So if we go like this, 1, 2, 3, 4, 5, 6, and I get the decimal point here, then I actually have 0.6574 as my answer. Now, one thing you want to remember is when we just write out a number like this, 6574, and we just write out a number like that and put mg here, we don't really know for sure if it's less than a whole million or more than a whole million, without some number, without some digit right there in the front of the decimal, then we don't know. Is it more than a million or less than a million? What is it? So you'll notice that when I'm writing the math out with you guys and I'm kind of showing you this, I'm going to put the 0 in place right here so that it's not anything more than 1 million. So it's less than the whole number of 1 million. So it's kind of important that we pay attention to that in purposes of reporting values to the state or to the federal authorities. When we're kind of filling out our monthly reports, they would want that as a whole number. And so putting the 0 in place is the common practice. So just want to kind of mention that to you all. And let's go look at the next example here. We have 6,700 gallons. So 6,700 gallons, again, divide by the number 1 million. I'm just going to put up the numbers here. I'm not going to put the units. So just remember, it's 6,700 divided by 1 million. And the units now are 0.0067 mg, just like we show here on the slide. That's what I got. And the number 0 in front of it represents it's less than a whole number. And again, if we're rounding here, you may actually say 0.00. And if we were going to drop off that 7, it would force the conversion of this number 6 just to the left of it to become a 7, because the 7 is greater than a 5. So we would actually report that as a 0.007 mg. I kind of messed up here on my slide, kind of moving forward. So this is mg. All right, so that's how we would report that. Now, if you want to be the most accurate when you're working the math, then keep the number intact as you can, and you would be more accurate than if you rounded it. So again, it's not a problem to be more accurate. I'm just saying that you'll still get a very close answer regardless. All right, let's try. I think we have one more here, and here's another example. So we have 27,563.8 gallons. So remember, we have a decimal point here. Move the decimal point 6 places. 1, 2, 3, 4, 5, 6. Decimal point ends up 6 places over. Notice that there's nothing here in this space. We need to fill that in with a 0 and put a 0 in the front so we know it's less than a whole number. So we have 0.0275638. Now, again, going over to the right side here, we have all these digits. Do we need to keep all of those digits? So if we were just going to go out to the, say, 3 decimal places over, 0.02 what? So we're going to get rid of the 563, but this 5 is 5 or greater, and it's going to make that 7 become an 8. So that's how we round, and that would be then million gallons. So 0.028 mg would be equivalent to what we show here on the screen. And I hope that's helpful for you guys. That is important that you do recognize this, because we're going to be working some math here in just a little bit. That is pounds formula, and the pounds formula requires these to be in mg units. So we certainly don't want to mess that up. What about converting million gallon units, say, backwards? What if we had to go from an mg number backwards, because the formula says, hey, I want this to be in gallons, and you just figured out million gallons? Well, how do we go back to the gallons? So we would simply multiply our number by the number 1 million, would actually put the zeros back in place. So it's a way to actually, make it back into a gallon units. So here we have an example. We have an example of 0.035 mg. So multiply that number by 1 million. Kind of put it here, 1 million, multiply by 1 million, and you end up with 35,000 gallons. It just moves the decimal point actually 6 places over to the right, and you put the zeros back in place. So 35,000 gallons is the equivalent of 0.035 million gallons. What about this example? So we have 6.76 mg, so 6.76 million gallons. Move the decimal point 6 places over, or on your calculator, multiply. 6.76 multiply by 1 million. Put all the zeros in, and I came up with 6,760,000 on my, oops, I just hit a button by accident. And I wanted to show you that that's what I came up with. And I multiply that and divide it. So, okay, so here we go. I came up with that same number, 6,760,000 gallons. Pretty straightforward. Hopefully, you guys can kind of see that and picture that and how that would be useful. All right, so that concludes part 1 of 7. And I'm going to take a break and give my voice a rest here and get a sip of coffee. And I recommend you guys stand and stretch and get ready for part 2, because that's what we're moving into next, obviously. So I'll see you after a short break. So I'll catch you on the flip side. All right, welcome back. Hopefully you had a good break and you're ready to continue on with Water Distribution System Mathematics, Part 2. This is where we kind of start getting into the more of the volumetric things like cubic yards of stuff and soil that's being removed or asphalt and all that kind of fun stuff. So we're going to get into some additional things. So calculating dirt, cubic yards of concrete, gallons of paint, tons of asphalt. So whether you're taking a level 1 exam, a level 4 exam, or if it's a distribution class A or distribution class D or whatever level licenses you're taking, this is really good stuff. And you would need this in the field as well as just for exam prep. So let's dive into this. So we're going to use some of this applied math now. First things first, remember that a cubic foot, a box that's a cubic foot shape, is essentially 12 inches by 12 inches by 12 inches. So it's a three-dimensional shape that is in inches, 12 by 12 by 12 inches. That's a cubic foot. Now, if you have a cubic yard, then how many cubic feet, boxes, would fit into a cubic yard? Think about this. This is now it's a shape, it's a large cube that is essentially 3 feet by 3 feet by 3 feet. So multiplying these together, multiplying these three across, 3 foot by 3 foot by 3 foot, 3 times 3 times 3, I get 27 cubic feet in 1 cubic yard. A yard is 3 feet long. So a yardstick 3 feet by 3 feet by 3 feet would be 27 cubed feet. So here's a box. This is 1 cubic foot showing on the screen. And I should be still sharing the screen. I'm just going to double check something here real quick on my settings and make sure I have everything working correctly so that you guys can still see. That sounds good. So I'll make sure during my break I didn't mess something up. All right, so we got 1 cubic foot showing on this slide. It's 1 little box right there. You can kind of see. I'll go back and make sure you kind of see what I'm talking about here. So here is what I'm talking about, 1 cubic foot. And if we're talking about 27 of them making a cubic yard, it would look something like this. Go 3 foot this way. That's 3 feet, right? That's 3 cubic feet. And then pile it up like that. Now we put 3 foot this way. This is now 3 feet this way. It's 3 feet this way. Right? So now we have 9 cubic feet. And let's put a box of shape like that in front of it. So that's another distance here. This is only 2 feet over. We need to go 1 more foot out to make this be a cube. So there we go. This is 27 cubic feet is 1 cubic yard. So this is 3 feet. This is 3 feet. And this is 3 feet. So it's a cubic yard. Now, why is this important? Well, we get concrete. We order concrete as cubic yards. We take soil away from the job site in a dump truck, and the dump trucks are based on cubic yards in the dumpsters or the dump box or the dump container itself. So, you know, everything in some of these cases that we deal with, a lot of these are in cubic yard increments rather than cubic feet. Another way you can look at it is if you go back and remember the old Rubik's Cubes and think about this Rubik's Cube as a toy that we used to kind of play with way back in the day, kind of showing my age, right? Just imagine if that was 3 foot by 3 foot by 3 foot, that'd be a cubic yard. So that's my example. All right, so this question says, how much dirt is there? So how much dirt would be removed in cubic yards? We call it spoil or the leftover material. How much dirt or spoil will be removed from a trench? And the trench is 80 feet long, it's 6 feet wide, and it's 5 feet deep. So how many cubic yards of soil were excavated from this? So what we need to do is remember that there's 27 cubic feet in 1 cubic yard. So here's how we work this out. I put the units here. We had an 80-foot trench. Let's see over here. We had 80 foot here, 6 feet here, and 5 feet here. So let's go to the next slide and make sure we have those numbers. So it's 80 feet long, 6 feet high, and 5 feet wide, or reverse. And let's do that math and make sure we get that cubic feet. So 80 feet times 6 feet times 5 feet. I got 2,400 cubic feet. Remember, that's how we do cubic feet. That's volume. That's basically the volume formula. Now what we need to do is convert the cubic feet into cubic yards using the 27 cubic foot conversion factor. So 2,400 or 2,400 cubic feet, divide that by 27 cubic feet per cubic yard. And now I'm coming up on my calculator. I do have 88.88888 goes right along. So it's a 88.9 cubic yards. And if you really want to just round up, because cubic yards and dump trucks and all that stuff, we don't have to be super accurate as far as the tenths go. We could just say 89 cubic yards of total soil would have to be removed, or you've excavated that many cubic yards out of that trench. So that's how you work that out. Main thing is, don't forget the conversion factor of 27 cubic feet for each cubic yard. Remember, the dump trucks and stuff generally come in cubic yard capacities in these trucks. So how do we apply this into another situation that might be something applicable to an exam, or just in life, as an operator out there and you're trying to repair something that had to be, water main broke, and let's say you had to remove a whole bunch of concrete from a sidewalk. So concrete would also be ordered in cubic yard increments. So remember to convert any inch units that you are faced with, convert that into feet so that everything is in the right units to start with. Remember, we're trying to work towards cubic yards, and we can't have cubic inches mixed in with these feet units because we're trying to get cubic feet into cubic yards. So we have to do the conversion first. Any inch numbers have to go into inch numbers have to go into feet units first. So it's a refresher. Here's a refresher. We have 4 inches. How many feet would that be? So, 4 inches divided by 12 inches per foot. So 4 divided by 12, I got 0.33333333. So this one goes off to 0.333. So let's go out to the second decimal point over and say 0.33 feet. How about 9 inches? So we have 9 inches of height, or 9 inches to convert into feet. So 9 divided by 12 inches. So 9 inches divided by 12 inches. 9 divided by 12. I get 0.75 feet. So 3/4, this is 3/4 of a foot. So 9 inches is the same as 0.75 feet. How about 16 inches? Remember, we had a pipe diameter that was 16 inch. We'll convert this into feet units. So 16 inches divided by 12 inches, 16 divided by 12. I get 1.3333, and it keeps right on going, right? So 1.33 feet. So hopefully that's a good refresher, kind of knock some of that rust off your mind when you're working through some of these inches. Don't forget to do that, because in some cases you may see answer choices with really large numbers, that is using the inches as inches rather than converting to feet. And the second thing is that if you're in charge of ordering concrete or asphalt or something to that effect, you certainly don't want to order, let's say in this case, 4 feet of asphalt, because you didn't convert the inches into feet, because we're not pouring concrete into a sidewalk that's 4 foot thick. It's only 4 inches thick. So you could order way too much concrete and you might get in trouble. All right, so here's our first example of this. We have a sidewalk that must be replaced after a water main break. The sidewalk is 35 feet long, 4 feet wide, and they want it to be 5 inches thick. Okay, so we're meeting some standards that say how thick the concrete sidewalk should be. How many cubic yards of concrete will we need for this? So first off, this is in foot units. That looks pretty good. The 4-foot width is in foot units. So let's say it's 4 feet across. That's pretty good. And let's say the total distance was 35 feet. That's pretty good. But what about this distance right here? Remember, the distance is the thickness of the concrete. It's not 5 feet thick. It's 5 inches that we need it to be. So we have to convert this inches into feet units. So remember how to do that. 5 inches divided by 12 inches per foot. So 5 divided by 12, I actually now have 0.41. I get 0.4166. Let's just say 0.42 feet. We'll go with that. Okay, so this distance now is 0.42 feet instead of 5 inches. All right, inches to feet. I just showed you that, 0.41666. We can say 0.42. And now how much concrete? We can now work cubic feet first. The first thing we're gonna do is cubic feet. So 0.42 feet, which is the thickness, multiply by the 35 foot length, multiply by 4 feet as the width. And what do we get for this? So 0.42 multiply by 35 times 4, I get 58.8 cubic feet. Let's see if we have the answer for that. Ah, we do. We have the answer showing there already. So 58.8 cubic feet. All right, so 58.8 cubic feet. Now we need to convert that into cubic yards. So 58.8 cubic feet divide by 27. And now for cubic yards, I have 2.1777777. And I would say, you would probably round that just to 2.2 cubic yards. And that's all we would need. Now, if you weren't paying attention and you didn't do the conversion of this thickness, you would come up with a much greater number of cubic yards, and you would be seeing concrete trucks, down the road delivering, way more concrete than you would need for this job. So somebody's going to pay for that, right? They mixed up the concrete for you, and they're going to charge you for it. So watch out for your calculations here. All right, let's move on to another concept. How about tons of asphalt? If you have a roadway to repair and now we have to order some asphalt, they may ask you for cubic yards of asphalt. They could ask you for tons of asphalt. Let's figure out what this is. Now we need another conversion factor. We need to know how many pounds are in a cubic yard of asphalt or cubic foot of asphalt. We need to know how many pounds it weighs, but we would be given that information so we could work this out. So here we have tons of asphalt. We're going to apply some pavement to a roadway or repair that we're making. So we're going to order it by truckloads, right? And hopefully it doesn't do this and spill out all over the place, because that would be a bad day at the job site, wouldn't it? So the reporter would say to you, how many tons of asphalt were spilled all over the ground? And hopefully you would be able to calculate that. So here we have an example. It says, how many tons of asphalt will be needed to repair the roadway? We've got a roadway repair of 100 feet long. We're going to repair a 45-foot wide, width across. The asphalt should be 6 inches in depth. And the density of the asphalt, by the supplier is 145 pounds for each cubic foot of asphalt that we're going to be dealing with. So we have the actual pounds per cubic foot density number that we can calculate this with. So let's go ahead and work this one out. So we have the inches that need to be converted to foot units first. Remember, 6 inches is the thickness, not 6 feet thick. We only need 6 inches thick. So 6 inches divided by 12 inches per foot. So I can write it out like this: 6 inches divided by 12 inches per foot. We already said this a little bit earlier from another example, is 0.5 feet. All right, so that's our first step. Next step, calculate the total cubic feet of the material that's needed. So for cubic feet, in this case, we know that we have a length, we have a width, and we have a depth of or a thickness. So it's not a cylinder, it's a rectangular shape. So we do the volume equals length times width times height. So we have 100 feet times 45 feet times the thickness of the asphalt is 0.5 feet. And for this, I have 2,250 cubic feet. All right. So that's what I got. And it looks like that's what we have on the screen. So I think we're doing good so far. So if you're working this out, if you're following along, I hope that you're also getting 2,250. And my units at this point are, there have foot units here, and we have 3 different foot unit values. So we are in cubic feet. All right, good, good to go so far. Now, remember that the density of the asphalt was given to us. Now that's where this comes in handy. We know that we need that many cubic feet. We know we need 2,250 cubic feet. And we also know that 1 cubic foot of asphalt is going to weigh 145 pounds. So how do we figure out the total pounds? So it's 2,250 feet cubed multiplied by the density or weight of 145 pounds per cubic foot. And let's see what we get. So on my calculator, I got 2,250 times 145. I came up with 326,250 total pounds. That's what they're showing on the screen. That looks pretty good. I think we're off to the races and we're doing good so far. Is that my final answer? The final answer is looking for tons, not pounds. So what do we have left to do? We have to pay attention to what the question's asking us. We need to convert this into tons. So we use a conversion factor of 2,000 pounds for every ton unit of measurement. So 1 ton is equal to 2,000 pounds. We're going to now divide, I'm going to kind of write it up here. We're going to divide the 326,250 pounds. We're going to divide it by 2,000 pounds per ton and do the math. So 326,250 divided by 2,000. And I came up with, let's see what the answer shows here. I came up with this number exactly on my calculator, 163.125 tons of asphalt will be needed to do the job that is shown to us. And this was, I think it was 100 feet long and 45 feet wide and 6 inches thick. So that's how many tons of asphalt would be required. That's it. Hopefully not too bad so far, right? So if you guys are good, if this is a little bit scary for you, go back and just kind of replay this and just watch out for those units of measurement. You know, make sure you convert inches to feet, and then you'll be all set. If you come up with a number that looks kind of crazy on your calculator, if you came up with something like 900,000 as a final answer, or some high number, some really high number, much higher than 163. If we come up with a really high number and it doesn't make sense, you think about this, like, would we really need that many tons of asphalt? If it doesn't make sense to you and it doesn't look right, then go back and check your math and watch your units. That's why I like to write this stuff out and kind of watch the units and what's happening with them. So we kind of pay attention to that. I don't generally teach the math where we're having to like divide by 1 and put all the units in and cross cancel all the units out. I don't teach it that way, but I'm hoping that it's okay for you guys to just kind of follow along and you can kind of see what we're doing here. But we are in a way paying attention to those units and know where we are at the end of the calculation. So that's the important thing, is to not forget that. All right, so let's keep right on going. So next concept is, guess what? The next concept is paint. Painting tanks and pipes. This is getting more challenging as we go through this. Remember, I said we're going to work from simple to complex. So now here we are getting into something a little bit more complex. So we're going to talk about painting tanks and pipes. So we got a storage tank that's painted and we have pipes that have to be painted. So let's cover each of these. So the question basically is saying how many total gallons of paint would be needed to paint, let's say, the interior of a ground storage tank. So you got to kind of imagine, if you will, what the surfaces are that we're trying to paint. In this case, if we're painting the inside of something, sometimes we paint the inside of steel tanks with corrosion resistant paint so that we're protecting the material underneath. So this question says interior of a ground storage tank, and we're using 2 coats of paint. And in this case, the number of gallons that would be used per covering would be given to us. So the number here on this slide, down at the 3rd bullet point, it says 1 gallon of paint can cover 230 square feet. So that number, where did I get that from? It came from the Tnemic website for suggested paint coverage at a medium thickness coating. In the notes, if you go into the notes parts of the math, or rather go into the notes pages of the Tnemic website for these different paints, they have a range. The thickness, if you're going to apply it in a thin or a thick or a medium coat, just depends on what nap rollers and stuff you're using. But if you're doing a medium thickness coat, they say basically 230 square feet per gallon of paint. So what we need to do then is figure out how many square feet we're painting, right? We're not filling the storage tank with paint, like filling it up with paint. We're just coating the surfaces with the paint. So we have to remember what we're dealing with here. We're only using surface area. We don't need cubic feet. The tank in this question is 110 feet in diameter, and it's 24 feet tall. So we're going to paint the interior walls. We're probably also going to paint the floor of the tank and potentially even the ceiling. So we have to pay attention to what the question is telling us or what you're trying to do on the job site. So here's our example. We have a 110-foot diameter and we have a 24-foot high storage tank. The formula that will be used for this is given to us on the formula sheets. It's on page 1 of the formula sheets, and the arrow, the red arrow on the screen, is pointing to the formula that would be needed. Now look at how much stuff there is in this formula. Now, first thing is don't panic. It's not the whole, you don't need every single thing on this formula, because remember, we have 2 ways of doing the surface area of a circular shape. You've got the pi r squared method, or you've got the 0.785 method. So again, you can choose whichever one you want. And let me just show you what we have. For the first example, it's the area. Remember, that's all we're doing is the flat surfaces, is 2 multiplied by 3.14 times radius squared. And the 2 is actually the bottom part and the top part. We're going to calculate the area of the discs of, let's say, the disc or the circular shape, the cross-sectional area of the floor, or the cross-sectional area of the ceiling that's round. So that's where the number 2 comes from. It's the bottom and the surface. If we're going to then also paint the sidewall, we're going to need to remember that there's something known as circumference, because we're going all the way around this thing. So circumference becomes important. That's actually what this is right here. The circumference is 3.14 times diameter. Now, remember that the circumference is just the linear distance around. If we multiply the linear distance times the height, like essentially if we flip this thing all the way open, we would have a super long rectangle to paint the inside of, and that would be where we would use the height. So I'm going to kind of show you this. We're going to break it into its own little segments here, and we'll go through it step by step. Remember, the other formula that was also used in this discussion is the 0.785 method times diameter squared. And again, that number 2 on the front there just means because we have 2 different cross-sectional shapes to paint. And then the second part of it is the same as the other one. So it's just the circumference times the height. So it's a lot of steps. There's a lot of things to do here, and you certainly don't want to mess this up. If you're going to order paint, then you want to make sure you get this right. If you're going to try to get this right on, say, an exam or in a quiz situation, you want to do your best at this and make sure you can kind of figure or conceptually see what we're trying to paint. All right, so let's take it step by step. So my first step, or my first segment of this, is we're going to say, let's do the inside ceiling and the bottom floor. Let's figure out the shapes, the circular shapes of those first. And remember, we said that there in the calculation there was two, and it's because there's a ceiling and the floor. So the 110 foot is where we need for the calculation. So remember, I'm just going to kind of show you what we're doing here. We're going to imagine, if you will, the ceiling and the floor as our separate shapes that we need. So here's the floor. So you need the surface area, the square feet of that circle, and the square feet of that circle. And we're going to basically figure those out first. So how do we do that? What's the surface area of a circular shape? Let me go back to that and move that out of the way. Remember, that's pi r squared times radius, or 0.785 times d. So you can go like this, 3.14 times the radius, which is half of 110. So half of 110 is 55. If you're not sure, just double check yourself. Divide by 2 and you get 55. So 3.14 times 55 feet times 55 feet is going to give me the surface area of the tank, of the circular shapes. So if you like the 0.785 method, it would be 0.785 times the diameter, 110 times 110. Okay, either one will give us a similar answer. So let's do 0.785 times 110 times 110. And I've got, on my calculator, got 9,498.5 feet squared. Now that is just for one of the shapes. That's just for one disc or one circular shape. So if you will, imagine up here at the top, I'm going to kind of write that number in, and we're going to say up here is 9,498.5 feet squared. That's the ceiling. There's another shape that we're going to paint, which is the floor. So we have to actually remember that we're doing multiply this by 2 because there's 2 of those shapes. So let's multiply that times 2. All right. So for total square footage, that this is number times 2, I've got on my calculator 18,997 square feet between the surface of the ceiling and the surface of the bottom floor. That's square footage done for that. So let's go ahead and move on to the next slide. I think we've got the little bottom floor drops out here, and now we've got those two things figured out. So there's the numbers. That's a tutorial showing you how to do this. We've got 2 of the shapes, and yep, that sounds like what I got on my calculator. I can still see it right there. Looks like we're good to go. All right, we're going to hold that number for later. We've got that part done. We're going to hold on to that number for a little bit later because we've got to add it to the actual outside, or rather the inside of the tank that we're also going to paint. So let's hang on to that 18,997. We're going to save that for later use. Now let's talk about the middle section. The middle section is kind of interesting. If you were to take a saw or cutting torch, whoops, get out of it, cutting torch, cut this down like this and flip this thing wide open, like split the sides or split the side and just lay it out, it would be a really, really long rectangular shape. And the linear feet, the distance here, this linear distance would actually be whatever the circumference is. And remember how to do circumference. Circumference was 3.14 times the diameter. So that gives us the circumference. That's the linear feet. So that's going to be some number here. And then if it's 24 feet here, this would be 24 feet. So from here to here is the width of it, and the distance, the length of it would be whatever that circumference is. So 3.14 times 110. So for the linear feet, I have now 345.4 linear feet. And how do I come up with square feet? How do I come up with area of a rectangle? Area of rectangle is length times width. So now what I need to do is multiply the 345.4 times 24. So for surface area of the inside, I got 8,289.6 feet squared. That's the inside wall of the tank. So far so good, I hope. You kind of imagine what we're doing inside these basins or inside this cylindrical tank, I hope. So now we have the inside part done and the wall. And now what we're going to do is, and by the way, this is all spelled out on the next slide here. So the formula is here, and that's what I just did essentially. And now we're going to add those two dimensions together. So we have total square feet. So from the previous discussion, we had 18,997 square feet. That was the top, the ceiling, and the bottom. And our middle wall section, or the middle shape around, was 8,289.6 square feet. So add these together. You notice on the formula, here's the addition symbols right there. There's where we're actually now adding these together. So the total square feet to be painted, let's work this out. 8,289.6. Add that to the 18,997. I came up with 27,286.6 square feet. And I hope I don't lose my Zoom connection here, because that's what I'm using to record this. I noticed that the sound might be kind of jumping around a little bit for you guys. I hope that it's not getting too out of sync, so to speak. So I came up with 27,286.6 square feet total to be painted. And let's see what we have for an answer. There we go. So it looks like we rounded just a little bit here and rounded up. At the very end, we rounded up. Now, I'm showing you this rounded up version, and we didn't do any rounding until the very end, so that we kept the numbers as intact as we could be at the end. So it's okay to kind of round at the end of a long calculation rather than in the beginning. If we rounded too early, we would probably come up with a little bit different number, a little bit further apart than where we really need to be. So I would say, for rounding purposes, save the rounding for the end if you can. All right, so that's the total square feet to be painted. Now, are we done? No, because that's not what the question was. The question was how many gallons of paint. So let's move on to the next part of this. Calculate the amount of paint. So we had 27,286.6 square feet to paint. And the Tnemec company's brochure for the paint that we're buying says that if we do a medium coat, then 1 gallon could cover 230 square feet. So how many gallons do we need? So we're going to divide the total square feet by the 230 square feet per gallon. So I've got that on my calculator, divide by 230. And in my calculation, I came up now with 118.6 gallons up on the top here, I'm going to put square feet and put the units here. Square feet is represented here, and this is gal per square feet. Oh, I got that reversed. I've got that reversed. It's square feet per gallon, right? Because that's what we're actually doing. So it's 230 square feet per 1 gallon of paint. So there we go. So square feet, cross out, we're left with gallons. So I came up with, and in this case, we'd probably round, what's going to be the difference if we just round up a little bit, we'll have a little bit, a teeny bit of paint left, right? So we had 120 gallons that we're going to order for our painting of the inside of the tank. So I'm using the inside of a tank. Remember, it could be the exterior. You just have to remember what you're trying to paint. If it's the exterior and it's just the outside part and the ceiling, or rather the roof, then you only have one circular shape to calculate, is the top, the ceiling or the roof rather. And then the middle section, which is the wall. So pretty straightforward, but a lot of steps. Remember, this may take you a little bit of while to do, so take your time with it and practice. Use these examples to practice with. If you know what the dimensions are of your storage tanks, plug your numbers in instead of using the numbers I gave you. Plug your numbers in and work the math out. All right, if we need 2 coats, then how many gallons do we totally need? We had 120 gallons, we rounded here. If we needed 2 coats, don't forget. So then we have to multiply the 120 gallons times 2, because 2 coats. So our total number here at the very end, total amount of paint, is 240 gallons for the 2 coats. All right. Hopefully you guys are good with that, and you can kind of picture what we're talking about and be able to work this out. Another particular calculation that's an interesting one, a little challenging, is when we're painting a pipe. And let's say we have a roadway crossing or a highway crossing with an overpass, or we have a river crossing with a bridge going over a water body. So we have some exposed pipe. We have ductile iron pipe or steel pipe that's exposed to the environment, and we want to paint this pipe to protect it. So here's an example of a water pipe that's suspended from a bridge over a water crossing. How many gallons of paint would be required to coat a ductile iron water main crossing a bridge that is 500 feet long and is 6 inches in diameter? Not the bridge, but the pipeline. So we have a 6-inch diameter pipe and it's 500 feet long. Each gallon of paint will cover 150 square feet, and we need 2 coats of paint. So we've got a little bit of work to do on this one. And again, if you're taking a higher level water distribution license, let's say if you're moving towards the class 3 or class 4 distribution license, maybe in Florida, a level 1 license, maybe a level 2 license, this would be an applicable question. So we've got it kind of broken down for you here on the next slide, and I'm going to go through it step by step to kind of give you an idea how we're going to do this. Remember, all we're doing is the outside surface area, okay? So first step is to find our formula. The cylinder or pipe formula is what we need. We're not doing a big ground storage tank with the inside surface area and all that. We're just painting the outside of this pipe. So the formula we're going to use is the area is equal to 3.14 times diameter times the length. Remember, anytime you got inches, needs to be converted into feet. Everything needs to be in feet units. So the pipe surface area for our example here is going to be 3.14 times the diameter in feet and the length in feet. I didn't give you the diameter in feet. I gave you the diameter in inches. So the first step is to convert the inches of diameter into feet. So 6 inches divided by 12 inches per foot, 6 divided by 12 is 0.5 feet. So I'm going to put that here, 0.5 feet. All right, so hopefully you guys are good with that so far. Now we've got one part of it done. Go to the next statement and what do we got to do? We got to figure the pipe surface area in square feet. Follow the formula. 3.14 times the diameter times the length. Remember, 3.14 right here is actually going to give us the distance around, which is known as circumference. So the circumference times the length is the surface area. So 3.14 times 0.5 times 500 feet length, and I'm getting 785 square feet for pipe surface area. There we go. So sounds like we're matching up pretty good so far. 785 square feet. That's the outside of the pipe that has to be painted. Now, the next thing is to figure out the gallons of paint. Gallons of paint per one coat. In this particular case, remember that we're given 150 square feet per 1 gallon of paint, and we have 785 total square feet. We're going to have to divide to break this down into its smaller components. So 785 total square feet, divide that by 150 square feet each gallon. So in this case, when I do the division here, I got 5.2, and that is gals. Remember, square feet cancel out, and we're left with gallons. So I came up with 5.2 gallons per one coat for that pipe. We said we needed 2 coats on the pipe. Don't forget to read the question all the way through and finish this and come up with a correct answer. We need 2 coats. 5.2 gallons times 2. So let's go 5.2 times 2. I came up now with 10.4 gallons of paint to purchase for this job. What do y'all think? So hopefully that's manageable in your mind. You can kind of picture it, and it makes sense. The numbers that I've used are from like company websites that I found that have, you know, their paint will cover this, paint will cover that. Those are just numbers that I learned about in researching for this, and the tons of asphalt that we did a little earlier, all that came from company websites that supply these products to us. So that's where the values came from. So hopefully this is going to help you. And remember, we're talking about this more like an applied math situation rather than just some random numbers that may not mean anything. We're actually figuring out real stuff that you could use. All right. So again, going back towards the type of exam or type of situation that you might be working in, if you're a supervisor and you are the person in charge of, let's say, budgeting for this job to happen during this fiscal year or the next fiscal year, you know that during the next fiscal year, you need to paint a certain number of pipeline, or rather river crossings, pipes that are crossing over rivers. So let's just take this one step further and kind of move on a little bit. In the previous math problem, we calculated that we needed 10.4 gallons of paint to do the river crossing that was 500 feet long of 6-inch ductile iron pipe. And that was our scenario. If the paint is costing $87.50 per gallon, again, from one of the company websites, then how much would it cost us to paint this pipe? So how are we going to figure this out? We need to remember the 10.4 gallons total and how much a gallon of paint is costing. So what's the total cost of the paint for the project? We're going to take the 10.4 gallons, and we know the cost is $87.50, that's dollars per gallon. Then our answer will be 10.4 times 87.50. I came up with $910 for the project. So just under $1,000 for the project. So you're the supervisor of the job and you say this job needs to be done this fiscal year. I need to figure just under $1,000 per river crossing. And now we know it's $910. If you have several of these to be done this fiscal year, then you're going to account for that in your budgets. If you're contracting somebody to do this for you and you don't want to go out there and hang off the bridge and paint this, then this particular calculation will help you know how many gallons of paint would be needed so that you know how much to budget for and how much that the contract, the quotes that are coming in to get the job done, how many square feet need to be painted. If you don't know how to calculate this and they put in some number on there that they estimated and they're way off, you could be in trouble. You could be ordering way too much paint for what the job is, or they would order maybe way too much paint for the job and then cost you a lot more money, or maybe they don't get enough and they say, oh, we calculated wrong, we need a change order, we got to do this. So it's important to be able to recognize what's really happening with these units of measurement and what we're trying to do. So it's applied math, I would say, in its finest glory right here. And it could make or break the budget and make or break your fiscal year. It could make or break you as a supervisor. So just want to kind of put that out there. No pressure, right? All right, so this concludes part 2 of 7. I hope it was helpful for you. And like you're seeing in this picture here, some workers, this is in Iraq, picture was shared with me from a water plant operator building a water plant and distribution system for the base in Iraq. So I want to say thank you for his service and for your service as veterans. These are workers putting together the foundation of a water plant. So just want to kind of say that I appreciate this, and this math is really helpful when you have to calculate this kind of stuff. So here's a real world example, right? All right, let's take a quick break and I'll see you guys back shortly. Okay, back from a